Welcome back, everybody, to the new link. I see a number of people. I see, close to 60 attendees on the call, which is great. We are very happy finally to have Ishan. Again, apologies for the technical difficulties. Let me introduce our speaker and go on. What we're going to do is Ishan is going to go on till 2 p.m. Eastern, actually 1:59 Eastern. He's kindly just agreed to go 15 minutes over. We are recording this, so we will share this recording as well. If as the students have to step out at 1:45, we understand. We will share this recording. We will also share Ishan's recording from Fall 20. What Ishan will do is try to focus, give you the basic ideas of self-supervised learning, and then focus on the newer stuff so you can ask him questions. So let's prioritize interaction and questions because we already have recordings of Ishan from the previous year. Ishan got his PhD from CMU a few years ago, and since then has been a research scientist at Facebook AI Research, and has really been doing cutting-edge work in self-supervised learning, among other things. So we're really happy to have him. I will stop talking and not waste any more time. Go ahead, Ishan.
Thank you so much for having me. I'll try to basically focus a little bit on the newer stuff, and please just stop me whenever anyone has any questions. I can't see the blue jean screen, so just if you unmute yourself or however this works.
All right. I'll speak up when there are questions. People will ask it in the Q&A tool, and I'll interrupt.
Okay, sounds good. So before we get into like self-supervised learning, why has this sort of topic really, or unsupervised learning, been that sort of important for us? So the main difficulty has really been that getting real labels is very expensive and very difficult. So the ImageNet dataset, which is touted as like one of the largest labeled datasets, has about 14 million images, and it took about 22 human years to label all of those 14 million images. And 14 million by itself is not really that large a number. I mean, basically, like social media websites get about 300 million images in a month or 400 million images in a month. And so 14 million by that size is really a very, very small size of data. The other thing to note is ImageNet is limited to images, and it's also limited to concepts belonging to like noun classes in WordNet. So overall, even though we think it's a large data set, it's really limited both in terms of its size and the kinds of concepts it contains. So in general, scaling supervision is really, really hard. And so a lot of interest in the past, I would say like 5 to 6 years, has really been about using semi-automatic processes to get labels. So these things can basically be something like try to use hashtags. So whenever people upload a picture to a website, they associate some kind of hashtags with it. Those hashtags can serve as a source of supervision. You can try to use, say, GPS locations or some kind of metadata associated with images. Or what we're going to talk about in this lecture is try to use the data itself. So that's the reason it's called self-supervised, because the data itself provides supervision. So the key idea behind self-supervised learning is that you need to obtain labels from the data itself. And one of the standard strategies for doing this is basically that you take your data and you split it into two parts. So you have like observed data and hidden data. And then you try to predict some property of the hidden data or the hidden data itself from the observation. And so most of self-supervised learning in computer vision basically can be classified as trying to do this. And just the means of setting up this prediction problem, what is being observed and what is being hidden, basically sort of distinguishes most of the approaches. And that's the sort of meat of the problem. Like, how do you set this up? What are you hiding? How are you predicting it? So in the context of computer vision, self-supervised learning, when we sort of do this like first task, when we're trying to predict some hidden data or the property of the data, we call this task a pretext task. The reason it's called a pretext task is because it's not really the real task we want to solve. We want to solve an interesting task at the end of the day, like image classification or like video recognition and so on. We really don't care about solving this particular task that we've set up for the unsupervised learning. But the only reason we're doing this is so that we can basically learn features without having access to any labels. So just this pretext task is automated, we get automated labels, but at the end of it, we want to solve an interesting task. So we take the features that we get from this pretext task and then try to basically use them for some tasks such as image classification. And these pretext tasks can be set up using images, they can be set up using video, they can be set up using video and sound. And depending on basically the kind of data that you're dealing with, the pretext task varies, and the kinds of features that you learn also vary. So I'll run through a few examples very briefly about what kinds of pretext tasks exist and how they've sort of become popular and evolved over the years. So one of the first sort of pretext tasks that was introduced was in 2015. And in fact, the term pretext task actually comes from this particular paper. The idea was basically that you take two patches from an image, in this case, a blue patch and a red patch. And what you're trying to do is you're going to keep blue patch as your reference, and you're going to predict the relative position of the red patch with respect to the blue patch. Now, the red patch can basically lie in 8 possible locations. And so the idea basically is that you're going to solve an 8-way classification problem. So the input to a network is basically going to be the blue patch and the red patch, which goes through a CNN. You compute the embeddings for both of these patches, and then you feed these embeddings into a classifier that's going to solve a 8-way classification problem. And because you can essentially sample these patches free of cost, you don't really need human labels to do this. This is a self-supervised problem. All the labels for this particular pretext task can be generated automatically. The other sort of popular pretext task is something called solving like a jigsaw puzzle. The idea is that you take, again, the image and split it up into a bunch of patches. And now you shuffle these patches. So in this case, you have 9 patches, and you permute using one of the 9 factorial permutations. The idea is that given this sort of shuffled input, now you feed these patches into a CNN, and you ask the CNN to classify which particular shuffling was applied to the input. So it's again solving an n-way classification problem. Again, these labels can be obtained just by applying some augmentation to the data. You don't need human supervision. Another example is basically taking an image and rotating it by a rotation. So you can rotate it by 0 degrees, 90 degrees, 180 or 270. And the output is going to be, again, a 4-way classification. So you feed in the rotated image to the network, and all the network has to do is predict which particular type of rotation was applied to the image. Now, the reason something like this might learn a useful feature is because in order to predict whether a tree has been rotated by 90 degrees or by 180 degrees, the network kind of needs to learn to reason about what kinds of objects are present in the image. That apples, for example, say you imagine a scene of an apple on a table. If the apple is on top of the table, this is probably what is imaged most likely. So that's going to be 0 degrees. But if it's reversed, then it is going to be like a 180-degree rotation. So the network kind of needs to distinguish these types of rotations in input images and learn something useful about the world. So basically, up until 2018, I would say almost every year there were about 10 or 12 new pretext tasks being proposed, different variations of the things that I talked about. And each of them kind of improved performance, but it was still not very satisfactory. So what's really missing from these pretext tasks, or some folks also call this proxy tasks? So let's try to look at what's going on in this entire picture of doing self-supervised learning. We have this real, yes.
So maybe at this point I can ask a couple of questions that have come in. So your examples really helped. And I think one question, given those examples that came in, is that could you contrast self-supervised learning against weakly supervised learning, and just maybe describe the differences?
Right. So, I mean, these terms are kind of loosely defined, and what may be weakly supervised for certain people might be self-supervised for certain other people. So with in terms of what my understanding is that weakly supervised typically involves predicting some kind of metadata that was associated with an image. So for example, if you upload an image to, say, Instagram, you have with that particular image the location of where that image was taken, or the camera that took that particular image, or the kinds of hashtags that were associated with that image. So in weakly supervised learning, the problem is set up as trying to predict one of these metadata associated with the image or with the media from that particular media. So now in weakly supervised learning itself, there are like multiple variations, right? So if you predict hashtags are more informative because they're actually like typed by someone. Whereas if you predict something like a GPS location, it's weaker because GPS location is not really typed by someone. It's a very weak form of information. It's going to be like 2 coordinates, and that's basically it. So in weak supervision, there is some kind of metadata that's associated, whereas in self-supervised learning, you're just using the image or just using that particular video and audio. You're not really using some kind of other sensory information provided.
Yeah, basically using parts of the data to make predictions about other parts of data that you did have access to, but are pretending that you did. Makes sense. Go ahead.
Okay, so till now we've seen these pretext tasks, and if you think about what's really going on is that at pre-training, we are doing this self-supervised setup where say we're trying to shuffle these patches and predict the right sort of shuffling applied to them. And then at test time, or where we really want to use these features, are tasks such as image classification. And if you think about it really hard, it's not clear why predicting, say, the rotation of an image or why predicting the shuffling of an image should really help you solve like a very fine-grained image classification task. And most of it is really based on intuition, like what I described about rotation, the rotation task. A lot of it is really based on intuition, but at some point you can imagine for certain types of objects or certain image distributions, these things completely break down. And if you want to be like really cynical about this, it's almost like wishful thinking that you're saying that your pre-training task will generalize to fine-grained image classification or object detection and so on. So in general, the pretext tasks actually miss 2 key properties of what image features should be. So image features should really represent how images relate to one another. And the other thing should be that image features should be robust to nuisance factors. If you change like this, if you change the lighting in which a particular object was imaged or the exact color of that particular object, then the image feature should be robust to all these kinds of invariant, like all these kinds of perturbations. And if you think back about it, like the classical sort of image features such as SIFT or HOG are really designed for this property of invariance. In fact, like the I in SIFT stands for invariance. So invariance has been a very fundamental guiding property for most of image classification and matching kind of features. So about, I would say 2018, 2019 is when a lot of these pretext tasks, because from 2015 to 2018, people had been proposing almost new pretext tasks every conference cycle. And it was still not clear why things were working. There were some wishy-washy explanations, but it was pretty unsatisfactory in how like the performance was compared to supervised learning. So about that time, basically a lot of researchers independently realized that these 2 properties are sort of the missing ingredients. And we should really try to represent both of these properties when we're trying to design a pretext task or trying to learn unsupervised features. So the popular and most common principle for like the recent methods has basically been that your features should be invariant to certain kinds of augmentation. So in this particular slide, I'm showing you an image of a deer, and that image has basically been perturbed across like multiple different types of data augmentations. So really, we want to learn features f theta, where we're learning a function f parameterized by theta. We want f theta of I to be approximately the same as f theta of any augmentation applied to I. So no matter what augmentation I apply to this particular deer image, I should really get the same kind of feature. And this idea basically is really powerful and has guided most of the recent success in self-supervised learning. And why is it useful? Again, learned features basically are going to be invariant to nuisance factors of data augmentation, which is a useful property to have. Invariance is just a useful property to have in general. So if this is so simple to set up, if that equation looks so simple, why is there so much research going around in this area? Like, why can't people just solve it and set it up simply? So let's try to run through an example where we try to set up the simplest possible way of like learning invariant features. So in this case, I have an image. I applied 2 data augmentations to it. So it's the same deer image with 2 different data augmentations. I feed it to a Siamese network. What this means is basically that both the encoders that you're seeing in this picture basically have the same weights, they're shared weights. And then I get a feature for both of these images from this encoder. And I can just, all I want to do is basically impose that both of these features should be similar. And I can maximize any type of similarity. So you can maximize cosine similarity, minimize L2 distance, your favorite type of similarity measure. And then I basically get gradients from minimizing this loss function. I can backpropagate and I can update the weights of the encoder. So basically I've whatever condition I told you earlier has been satisfied. I have been able to say that f theta of I is the same as f theta of augmented of I, and I have this very simple setup. So I should basically learn very useful features, right? So it turns out that in practice, this doesn't work really well, because what ends up happening is you'll end up learning a shortcut solution. The shortcut solution, or the trivial solution in this case, is that f theta of I is a constant. It's independent of the image. So in this case, the encoder basically just ignores the input image and always produces the same exact feature. Now in this case, of course, it satisfies the equation that we have written above. F theta of I is independent of I, so it's the same constant, and so it's going to be the same value no matter the augmentation applied to the image. So it is satisfying this property of invariance, but this is not really a useful feature because it completely misses the first property. Image features should really capture how images relate to one another. So if a deer image is similar to another deer image, that should be captured. But if a deer image is not similar to an elephant image, that should be captured as well. And so f theta of I being a constant really does not capture that first property. So in reality, basically both of these properties are necessary to get a useful feature. So in general, most of the recent self-supervised research has been about how to avoid these trivial solutions. And all these methods are using the same exact underlying principle, that you're trying to learn features that are going to be invariant to these data augmentations while capturing some kind of relationship between images. But they just differ in terms of how they're minimizing the loss function and how they're avoiding this trivial solution of f theta being constant. So here's just a sort of brief slide talking about the recent methods that exist in this literature and how each of them are trying to do basically this trivial solution avoidance. So the first group of these methods are basically similarity maximization methods that try to maximize the similarity between data augmentation 1 and data augmentation 2. So the features that you get from two data augmentations, you just try to maximize the similarity between them. And to do that, you can either use contrastive learning, you can use clustering, or you can use something called self-distillation. The other group of methods is basically trying to reduce the redundancy between the features that you get from two data augmentation. So it's slightly different from similarity maximization, but again, it's still trying to do the same thing where the features from two augmentations should be the same. And in this category, we have like Barlow twins, BigReg, and there are more such papers this year as well.
Ishan?
Yes.
A couple of questions have come in that I think might be worth taking now. One is, so one question was, I understand how invariance is necessary, but are you claiming that invariance is sufficient? I imagine not, right? You're not claiming that invariance is sufficient.
So, I mean, this is the classic example of invariance not being sufficient, right? Yeah. Because in this case, invariance is necessary, but if invariance is the only thing that you're going for, then it's not going to be like, this is already showing you that it's not sufficient.
Yeah, perfect. And I guess the second question is related to more recent work, or also related to classical work. The second question is, can we use a decoder to make sure that the features give back the original image to avoid the constant solution problem?
Yes, we can. So in fact, that's where I have a slide sort of talking about that. It'll come in a bit.
Sounds good. Perfect. Go ahead, Ishan.
All right. So these are the sort of categories. So let's quickly look at contrastive learning, sort of mainly because contrastive learning has been applied to a lot of different types of data modalities, and it's still sort of the more out-of-the-box solution is pretty robust and works maybe across like point clouds, video, audio, images, and so on. So it's been a very sort of robust solution. So the setup that we look at is basically going to be that most of these methods are going to work on ImageNet without labels. So they take the ImageNet dataset and they throw away the labels. And then most of them will take a network, for example, the ResNet 50 ConvNet, which is initialized completely randomly. And now you'll pre-train using that particular pretext task and contrastive learning and on this set of unlabeled images, and you'll learn some useful features. Once you have these useful features, how do you evaluate them? So you can evaluate them using transfer learning, where you take this particular learned representation of that learned network, and you transfer it to a downstream task where you have certain labels. So for example, we can just take ImageNet itself. So we can first do a pre-training step on ImageNet without using labels. And then in the second step, when doing transfer learning, we can add labels to ImageNet and then transfer on ImageNet using labels. Now, this particular type of transfer learning is actually hotly debated. There are various kinds of evaluation methods that you can use. One is to basically fine tune all the layers of a network. So you fine tune basically the entire network. The other is to basically just take a linear classifier, just add a new linear classifier and just train that linear classifier while freezing the entire network. And the last is to say basically not even add a linear classifier, just use the features and try to do something like a k nearest neighbor. So what varies basically between these three types of evaluation is that in the first one, the entire network is being sort of updated. The entire weights of the network are being updated. In the second one, you're actually updating only the weights of the linear classifier. Whereas in the last one, you're not updating the network at all. All you're measuring is how good is that particular feature representation at measuring things which are dissimilar and things which are similar, and how much does that correlate with my particular downstream task. So all these three different types of evaluation actually capture very different properties of the particular representation. And in fact, this is actually a very hot area of debate. If you look at the sort of community, people really don't seem to agree on which is the right evaluation. So, for example, if you look at the k nearest neighbor approach, that people argue that that's really measuring the feature because it's not updating the network. Whereas if you look at the full fine-tuning approach, people argue that it's really evaluating the initialization provided by the self-supervised learning. So it's not really about the features, it's about the initialization. And so basically, depending on what method it is or what you think about it, people basically use different types of evaluation methods. And in fact, this brings me to the sort of great spiral of research where things basically, you keep revisiting the same things by learning on what's going on. So, for example, pre-2015, people used methods like sparse coding, RBMs, and contrastive learning was actually popular back then. In 2015 is where these pretext tasks basically started coming in, where what I talked about, where you set up like patches or rotation of an image and so on. 2018 and 19 is where people basically started looking at invariance using contrastive learning. So contrastive learning became cool again, which was not the case. In 2020 is basically when non-contrastive methods sort of started becoming popular. And actually more recently, pretext tasks are cool again because people find that actually we want to evaluate things by full fine-tuning because all we care about is initialization. So pretext tasks are okay for that. That's actually what I'll be talking about at the end of this lecture. So just to sort of remind you, there is no clear, there is no one answer for everything. And in fact, as we learn more and more, we kind of spiral down and make more progress and basically keep revisiting the old ideas, but just using the learnings that we have with our sort of recent methods. All right. So let's look to sort of position back where we were. We were looking at contrastive learning, and we're trying to basically see why contrastive learning might be useful. So I'll talk about one paper that we had called Pretext Invariant Representation Learning, where we tried to relate contrastive learning with pretext tasks. So one slide summary of contrastive learning is that it tries to basically learn features that are able to relate, that are basically able to learn good representations of related items and unrelated items. So in this particular slide, we have the blue items, which are related to each other, the green items, which are related to each other, and the purple items that are related to one another. And in contrastive learning, we basically compute an embedding for each of these items. So you feed in, say, an image, a blue image, and you get a blue embedding from it, and a purple image, and a purple embedding from it. And the idea basically is that your loss function is going to try to minimize the distance between related features, and basically while sort of pushing away the unrelated features far away. So in this case, for like the example on this slide, the distance between the blue embeddings should be much smaller than the distance between the blue embedding and the green embedding. And the same thing, basically, the distance between the blue embeddings should be much smaller than the distance between the blue embedding and the purple embedding. And now a reason why this basically does not collapse is because, for example, imagine that all the embeddings became the same. The trivial solution is basically that all the blue embeddings and purple embeddings are essentially the same exact value. In that case, this inequality is not satisfied because the distance between all these embeddings is basically going to be equal. And so this inequality does not get satisfied. And so contrastive learning basically uses this notion of positives, which serve as an attraction force, and negatives, which serve as a repelling force to make sure that the representation does not collapse. And it's actually a very robust way of ensuring that collapse does not happen. So coming to PIRL, in PIRL, the way this happens is basically we create these related items by just using the pretext task as a data augmentation. So you have your original image and you basically apply a pretext transform. So in this case, say a jigsaw transform or a rotation transform. And that creates a pair of images, image I and image IT, which are basically the same image, just a pretext transform has been applied to both of them. And what we do is we basically ensure that the representation from both of these images should be similar. And we use a contrastive loss to ensure that. So now this representation ends up basically becoming invariant to the pretext transform. So unlike a pretext task, where the feature needs to predict what type of jigsaw rotation was applied, in this case, we are telling the network to explicitly ignore that. We are saying that no matter the jigsaw or the rotation transform being applied to your input, make sure that the feature that you get from it is the same as the feature that you get from the original image. In some way, it's basically completely ignoring the sort of jigsaw transform being applied to it. And so to put that basically in this kind of picture, the related items basically in contrastive learning for PIRL come from an image I and the sort of jigsaw transform being applied to that image I. Whereas in the case, basically by changing this definition, we can get different types of methods. Now, how do we get the unrelated items? We basically just treat the entire data set and all the images in the data set as unrelated items in this case. And so all of those basically serve as the negatives in contrastive learning. So one good property of basically looking at things in this way is that if you just were to inspect the features that are learned, so in this case, what we're doing is we take a ResNet 50 and we look at features at different layers of the ResNet. So Con1 is the layer that's closest to the input, and Res5 is the stage that's basically closest to the output. And we're going to basically just take the feature that we get from each of these layers and learn a linear classifier on top of it to measure how good this particular feature is. And we're measuring this on ImageNet 1K in terms of its classification accuracy. So in the green line, you basically see the jigsaw method. And what we observe is that the feature, as you get deeper into the network, you basically get an improvement in performance, which is to be expected because as you get deeper into the network, the features should become more and more semantic. But basically, as you get towards the last layer, the feature becomes less semantic. And that's basically because you're predicting something which is not correlated with your downstream task. You're predicting a jigsaw transformation, which has very little to do with recognizing the classes in terms of ImageNet. Whereas in the case of PIRL, what we see is basically that the representation quality keeps improving as you keep going deeper into the network, suggesting that invariance might be a useful property to sort of build in. Now, like I said earlier, depending on the type of positives, the definition of your positives or the definition of your negatives, you can get various different types of contrastive methods. So, for example, in CPC, what the author says basically that all the patches that are close by in an image are positives, and all the patches that are far away in an image are negatives. For methods such as instant discrimination or MoCo or SymTheor, the idea basically is that patches coming from the same image are positives, whereas patches coming from a different image are negatives. The same idea can be applied to frames of a video, basically that frames in a video that are close by are positives. To video and audio, that the video and its corresponding audio are positives, audio coming from a different video is negative. You can apply that to patches, basically saying that if you track a patch in a video, all the patches that belong to a single track are positives, all the patches that belong to a different track are negatives. Basically, this entire definition of positives and negatives is up to you, and basically by defining this particular definition, how you consider your positives and negatives, contrastive learning can be generally just applied to most data modalities pretty easily. You can also do that
Ishan,
yes.
A quick question here. So I think people understand, that you want positives to have low distance and negative to have high distance. Can you say a bit more about precisely what that loss function is that you write down to enforce this?
Yes.
Like, what is the loss function that we're minimizing here?
So it's a non-parametric softmax. Basically, Okay, there are multiple. I'll start with the simplest version because that's actually easiest to understand, whereas what's done in practice is going to be slightly complicated. So, in the simplest version, basically is going to be right. So the simplest version is basically going to be something like a triplet loss. So the idea basically is that you say that the distance between the blue items, so distance between A and B, uh, minus basically the distance between B and D, where D is the negative, should be less than a particular margin. Or the distance between A and B, where A and B are related, should be less than a particular margin. So essentially, you just set up a margin saying that the distance between the positives and the distance between the negatives should be within this particular margin of one another. And that's it basically. It's a cosine distance between the two embeddings.
Yeah,
The sort
and
of more
for sorry, I was just going to add for the class's benefit that you folks have seen the hinge loss in the context of multi-class logistic regression and SVMs. And so if you remember, that hinge loss also has a margin concept, and what that means is that beyond that margin, the gradients become zero. So that's one way of relating this. But really the difference in the distances, and the distances computed with cosine similarity is cosine similarities of the embeddings of two different images are what Ishan is computing. Go ahead, Ishan.
And the sort of more complex version of this is something called like InfoNC or NC, which basically is a non-parametric softmax. The idea basically is that you consider, rather than just one negative at a time, you consider say 5,000 negatives. So all you're going to do is basically you're going to say that the distance between the current point and the positive should be smaller than basically the distance between the current point and all of the 5,000 negatives. And so rather than setting it up as basically different types of binary problems, you set it up as a single multi-class classification problem. So that's basically the InfoNC loss. But the idea basically is always about cosine similarity of embeddings.
Sounds good. There's one other question that has come in, Ishan. Do you know how these similarity and dissimilarity learned techniques compare to classical techniques before deep learning in computer vision? Because I imagine this is something like, duplicate detection is a well-solved computer vision problem. Can you contrast it against that set of methods?
Right. So compared to something like SIFT or like SIFT basically is again like a very popular feature for retrieval, so it is going to be very good at finding duplicates. These methods actually do surprisingly better. So I think the main reason basically is that because these features are learned for the particular type of image distribution. So for example, SIFT when it was designed for certain types of low res, or depending on the type of images, SIFT may not really work on a very different image distribution. The advantage of doing it in this particular way is that you can adapt very easily. So you can do this basically say on medical images as well. So in that particular case, the default parameters for SIFT may not really translate very well to say MRI scans. Whereas in this case, if you just set up the learning problem right, you can actually get a pretty reasonable feature quickly.
Sounds good. Thank you.
All right, so I have about 20 minutes. I'm going to actually try to move very quickly and skip over most of the things that I had because I want to get towards the end of it. And then I'll rather take questions than try to go over these slides because most of it is actually going to be very similar to what I've covered earlier.
Sounds good. And I think the newer stuff in general will be of interest to people because they haven't seen it.
Yeah. All right. So basically, this slide is like a one-slide summary of what these different techniques for preventing trivial solutions do. And so the first three sort of categories that we see over here are basically techniques that are trying to use some kind of asymmetric learning. So you have a Siamese network, but you're basically not really propagating the gradients to one branch, or there is some kind of difference in the architecture between the two branches. So for a long time, people thought that this was very critical to prevent prevent trivial solutions, but recently these sort of redundancy reduction-based methods have shown that this is not really the case. You can actually have a very symmetric branch where you are learning features and actually updating both the branches in the same way. It's just that if you change your loss function slightly, things basically become well conditioned and you actually don't get into these trivial solutions. All right. So the things I'm going to jump around once more because I just want to cover one thing that people may not have seen, and then I'll be done.
Perfectly fine.
Okay. So the one paper that was somewhere in between, basically in the order of things, is Dino, which maybe some of you have seen. The idea in Dino is basically, again, it's about self-supervised learning, where we have an image, we take two data augmentations of it, we feed it through an encoder and a momentum encoder, where the momentum encoder is basically just the moving average of the weights of the current encoder. So all you do is just keep a running average of the weights, and so this momentum encoder never gets updated with backpropagation. And now the features learned are basically just trying to maximize the similarity between the one data augmentation that you get and the features that you get from the blue encoder, and the features between the augmentation number 2 and the features that you get from the teacher encoder. And so in this case, the main sort of thing that we changed was actually switching to a transformer. So in a transformer, the sort of key idea is that you take an image, you split it up into a bunch of patches, and then you feed these patches independently through a series of layers. I'm not sure if the class has actually seen a transformer. How much detail I need.
They have seen attention. They have not yet seen self-attention. And they have not yet seen transformers. It is coming 2 lectures from now. So for now, everybody in the class can just assume that it is a particular layer that converts embeddings of patches to more other embeddings. So you take a patch and a sequence of patches, and you're getting embeddings for each of these patches. And for the context of Ishan's description, that may be sufficient. We'll tell you exactly, we'll peer into the layer and tell you the details in 2 lectures.
Okay. So the one sort of big difference between a transformer and a CNN is, so in practice, I mean, apart from the self-attention and apart from all of this, in this particular architecture has really been that in a transformer, at least the vision transformer that we use in this work, there is no notion of pooling. So whereas in a CNN, what ends up happening is you start with a large resolution image, you apply some kind of convolutional filters to it, then you apply a pooling operation. Then you apply more convolutions, you apply more pooling. And so progressively, as you go deeper into a CNN, the feature, like the height and width or the resolution of that feature map becomes smaller and smaller. So in the top image. Whereas in a vision transformer, one of the key things is there is no pooling. So you start, whatever input resolution you start with, that's the input resolution you end up with. And so there is no pooling when you're basically doing this kind of learning. The good thing about this is that, say in the top part, if we were doing unsupervised learning on that sort of small feature, the network never really has access to the big sort of pixels. It always works on this globally pooled sort of low resolution feature. Whereas in a transformer, the network ends up working on this very high resolution feature map when it's doing this unsupervised learning. So because of this, what we observed is that segmentation automatically emerges in a self-supervised network. So in the case of Dino, what we do is we basically look at the attention map of the vision transformer for a particular image. So in this case, there are 4 images, and on each image, we basically are looking at the attention map. And note that this particular network has never seen a label. It was trained in a completely self-supervised or unsupervised way. And what we observe is that basically when the network is computing its sort of global feature, the CLS token feature, it's always paying attention to the most salient object in the image without ever having access to any labels. And like my best guess for this is basically because this entire network, when it's learning in a self-supervised way, is actually operating on feature maps that have never been pooled. And so it automatically learns to figure out which pixels are actually the most characteristic of this particular image. Whereas in the case of a CNN, when we do this like a big amount of pooling, we never really actually have access to the sort of discriminative pixels. The same thing actually tends to happen that basically when we look at different heads of that particular network, we find out that different parts of the network focus on different parts of the image. So for example, in the clock tower, the network actually is able to figure out that the face of the clock, the flag, and the clock tower itself are actually 3 different things. So it actually learns to separate them out as well, which is a cool thing that basically emerges completely in a self-supervised way. And now this brings
Ishan,
me. Yes.
Can I ask a question here? So for the context of the class, I think I should emphasize these results were really cool and they were really surprising in the community because as Ishan stressed, there are no labels here, right? You've never seen that these images contain a bird or a building. All that these images have been trained for is similarity to other to augmentations and dissimilarity to other images. So the idea that segmentation emerges from that was very surprising. But Ishan, my question to you was how do you contrast this against some of the work that Antonio Torralba and Bolle Zhu did, where they showed that part detectors and object detectors emerge in CNNs trained for scene classification? So in that case, it was not a self-supervised learning approach. It was a fully supervised learning approach. They were trying to do scene recognition, but those CNNs contained max pooling layers and part detectors emerged. So perhaps how does that relate to your hypothesis that really max pooling was the problem?
So I don't think it's I should rephrase. I don't think max pooling is the problem. It's just that if you don't have pooling, it's much easier to get these things out. That's the main hypothesis. So I think like similar things will exist in a CNN. We actually quantified it in the paper. Basically, what we do is we just take these segmentation maps and evaluate them in an unsupervised way. And what we find is basically that in a transformer, these segmentation maps tend to be far more semantic. So you can actually just literally take this and run it on like Pascal VOC 2007, the segmentation challenge, and you get a pretty reasonable number without like training the network. Whereas I think that's the sort of more surprising part about it. So part detectors emerge when you do supervised training. Similarly, like saliency will sort of emerge when you do supervised training. But the saliency that this particular network captures is very different. For example, in this particular slide, ImageNet has a class of a flag. Okay, so this particular image that we are seeing is basically a flag image. What we observe is that the supervised network tends to focus just on the flag itself, where it will completely ignore the clock tower because there is no clock tower class. Whereas in this particular case, the network is actually focusing on all the things, right? Because it was never told to focus on a flag.
Yeah, makes sense. And a follow-up question: can you say qualitatively what the representations or the activation pattern or tension patterns from a CNN trained to perform the pretext tasks on these tasks look like? So the transformer captures nicely the salient object. What do CNNs capture?
So CNN will be like on very clean images. Let's see. Yeah. So there are examples we have in the paper, but on like very clean images where you don't have a lot of clutter, basically it will work pretty well. So for example, on the boat, it will work pretty well. But when you talk about like the bird on the top, it's going to be harder, just because whenever there is a lot of color or whenever there's a lot of clutter in the image, the CNN feature maps don't seem to be very good at like isolating the object. So for example, in the paper, we have like this picture of a motorbike with a lot of graffiti in the background. And so the dyno model basically is able to figure out that the motorbike is the object of interest. Whereas if you look at any supervised or CNN-based method, they tend to focus on the graffiti as well, because the graffiti has a lot of color and texture common with that particular.
Got it. Thank you.
All right. So this brings me to the last part of the lecture. Right. And so we go back to this spiral of research, basically that pretext tasks are basically becoming cool again. And why is that the case? So let's just try to look at that. So one of the sort of standout papers in this area has basically been BEIT, which stands for BERT, Pre-Training of Image Transformers. And the idea is very simple, and it's actually an idea that has been tried multiple times by multiple people. It's just that in this case now the machinery exists and these authors really figured out how to make it work really well. So the idea is straightforward. You take an original image, you cut it up into a bunch of patches, and you mask some of the patches randomly. So in this case, the gray patches denote a patch that has been masked. And now you feed in this masked patch image into a model, and you ask it to predict all the patches, so including the masked ones. So the idea basically is that the model should be able to figure out by looking at the unmasked patches what are the objects in the image, and just by reasoning about that, it should be able to predict all the masked patches. In this case, it can look at the foot of the dog and figure out that, oh, this is actually a dog in this picture, so probably the masked patch on the top is going to be its face, whereas the masked patch in the bottom is going to be its foot, and so it should be able to basically fill all of this out. And this idea is really common in NLP. Most of the NLP models that are trained really are trained on this fill in the blanks task, where you take in a sentence, a blank day, you feed it to a model, and then the model basically predicts whatever was missing in the blank, so sunny. And so you can see that it's basically the exact same idea that's applied to images, where you feed in the image with a bunch of like blanks, and then the model is supposed to predict what was is basically supposed to fill in the blanks. So how do you set it up in the case of images? For this particular architecture, what these authors did is they basically had this notion of a tokenizer. I know this class hasn't looked at VQVAE, but I'll try to give this sort of very quick idea of what this is. So a tokenizer basically takes a set of this particular image. So it's going to be like 255 pixel values for each pixel, and it will convert it into a set of discrete tokens. What I mean by discrete tokens is basically it's going to reduce the number of, it's going to quantize or reduce the number of possible values in that image. So in this case, if that image has basically at each pixel, you can have 255 possible values. In the tokenized world, at each particular location, you can only have 500 or only have 5,000 possible values. So it's basically just going to quantize it. So for example, a simple way of tokenization can be just to say that all the values of the image that lie between 0 to 100 are now mapped to the class 0. All the values that go from 100 to 150 are mapped to 2, and like 150 to 200 are 3, and so on. So essentially, you can convert this entire range of 0 to 255 into just 4 values. So this visual tokenization is just a smarter way of doing it, where you can convert that image into a set of smaller number of values. And so now what this model does is it takes this entire set of images and the masked patches and feeds it through a transformer. And the transformer is just going to predict basically what was missing in each of these particular masked patches. And so just by solving this particular task, the idea is that the encoder should learn a powerful feature representation. Now, how do you evaluate this? And we come back to the same question. Do we fine tune all the layers? Do we just train a linear classifier, or do we just do a KNN on top of it? So in this work, the only evaluation that these authors consider is full fine tuning. And basically they take that particular network and they fully fine tune it on ImageNet, and then they report the top 1 classification accuracy. What they observe is that their model is performing like really, really well. So in this case, the bottom row is basically the model proposed in this paper. The Dino model that I just talked about is basically right above their model. But you can see that their model is actually doing surprisingly well. It's actually on this particular benchmark, it's actually doing like 4 points better. With a comparable architecture, it's at least 2 points better. So this is pretty good progress when you talk about like accuracies on ImageNet. Now, the other really, really cool result from this paper was showing that basically because this network is trying to do this mask prediction problem, it actually learns very good segmentation features. So these authors take their network and fine tune it for the task of image segmentation, and show that in this case, again, the features learned are actually really, really good. So again, in the full fine tuning setting, this network is really good. But when you talk about the other types of evaluation, so linear classifier or KNN, it's really the features learned in this particular case are not really good. There are gaps of like 20 points or more compared to the Dino model. And if you think about why this might be the case, it actually goes back to the reason that I talked about for pretext tasks. Pretext tasks are solving something at pre-training time, which they hope will be related to the downstream task. So you hope that this masking or whatever that you're doing in pre-training is actually related to the downstream task. So the features that you learn may or may not be good for the downstream task. And so that's why you have to really fine tune them, because these features by themselves are likely not to be very good for the classification task. So you really need to fine tune them to be able to solve an image classification task. So that's why the linear classifier or the KNN performance for these methods is really not good. This idea has actually become like caught on very, very quickly. If you like go to open review for IClear this year itself, there are like about 10 or 15 papers that are really building on top of BIT. This is another paper that just came out that's basically taken the BIT idea and extended it to videos. The idea basically is that, again, you convert the video into a bunch of patches and you mask out a set of patches, and then you again try to predict what was masked out. This particular paper tries to kind of address this problem that the pretext task may not be useful. So they combine this mask token prediction with contrastive learning to basically get the best of both worlds. And they show some really impressive results. In this case, they fine-tune their model on these like temporally heavy action recognition datasets. So in this case, the videos are really long, and you need to reason about all the frames in a video to recognize the action. And so these are pretty challenging datasets in terms of recognizing actions. So the top row in this case is the previous state-of-the-art supervised method. So this is like a very, very nice, strong baseline. It's 65.4%. And in the bottom, you basically see Wimpact, which is this particular work. And you see that just by doing self-supervised learning, they're actually learning really powerful features. So from 65, they're basically getting to 68. And if you think about it, basically, when you're trying to predict these masked patches across a long video, the model really needs to reason about what is happening in a video to be able to predict these particular patches. And so it's this is the hypothesis for these authors, that by doing this mask prediction across a very long temporal range, the model learns features that are going to be very good for temporally heavy classification datasets. And again, there are no linear or KNN evaluations. And in general, this sort of brings us back to this question: is this representation learning, or is it learning a good initialization? And really, there is no clear answer. You can argue this question from both ways, and probably the middle ground is you try to fine-tune the model with as limited amount of data as possible to show that it's not only a good initialization, but it's also a good representation. So basically, by doing this, you can get the best of both worlds. You are showing that it's a good initialization while showing that it's a powerful enough representation, and you really don't need lots of labeled data to learn a good feature representation. So this brings me back to the end of my lecture. And basically, we start with pretext tasks. We go through all of this contrasted learning, and we find that people are again coming back to pretext tasks.
Great. Thank you, Ishan. So I know you have 3 minutes. We'll ask you 2 questions, and then we'll let you go. And I think we'll be able to fit it in. So one question is, in the methods that use data augmentation, aren't we injecting human knowledge via the choice of the data augmentation? So, and is there any research on how best to pick which augmentations to apply?
So totally. I mean, I think that's the sort of biggest cheat. Actually, even in pretext tasks, that's the sort of human injected bias, right? What should the size of the patch be? How do you sample those patches? That's really a lot of like design decision. And in fact, if you don't do things the right way, things basically don't work. So if you select a very small patch, that's not going to work. If you don't have enough data augmentation, things are not going to. So it is a lot of human injected knowledge. So it's not really unsupervised. In fact, if you argue this way, then the architecture that we are using is a ResNet 50 or a transformer encoder, which itself was optimized using some kind of supervised learning. So the filter sizes and so on were really figured out by looking at that data. Now, there is very limited research, surprisingly, into what kinds of data augmentations you should pick. And most of it really has to do with the fact that people are using ImageNet, where the objects are very nice and like big and in the center. And so basically, if you try like funky forms of data augmentation, things don't work very well. Because the object is going to be centered, it's going to be very large. So that really determines a lot of data augmentation that you apply and how successful that's going to be. And so if we if we move past ImageNet into like different image distributions, will we actually start to see that what data augmentations don't work and which one of them actually work. But so far there has been very limited interest in actually moving beyond image.
Got it. And sort of a low-level question, when people report the number of parameters of a model in a publication, do they only include the main classification model, that is the one used for the downstream task, or does it also include the pretext feature generator parameters?
They don't include the pretext feature generator parameter. It's only trunk. But, and the weird thing about it is basically like if you look at most of these methods, about 50% or 50% of the parameters are actually in that particular pretext generator part. So you just chop that off. That basically means that you reduce the number of parameters by roughly half when you're transferring it.
Got it. And I guess final question before we say bye to you. So we need good results only for. So do we really care about good results from the linear evaluation? Even if fine-tuning does well in order to achieve computational efficiency?
Right. So I think the main thing, that's why I like talked about the middle ground. I think the main reason for linear evaluation is basically that the feature itself is so good that you don't need to do anything, basically. So it's a very lightweight. The feature itself was so good that you barely needed to do anything to make it useful. Whereas with full fine tuning, you do need lots of data. For example, like the ImageNet, like this particular result, right? When you're fine tuning on ImageNet, you're actually using 1 million images again. So you can argue that, okay, you need 1 million images to show that your particular data, like representation, is good or bad. So I think the middle ground is really to show that what is the least number of images that you, least number of labels that you need. It doesn't matter what the evaluation methodology is, right? You can argue one way or the other for each one of them. But what really matters and why this entire field exists is because label data is hard to come by. So we should really start measuring the performance as a function of the number of labels being used rather than whether it was fine-tuned or whether it was linear or whether it was KNN. I think that those three things people can keep debating, and I don't think there's going to be any solution there. But what really matters is the number of labels that you're using. And I think that's actually the most objective measure there is.
Got it. Okay, so we're at 2 p.m. We'll let you go at this point, Ishan. Thank you for staying over. Sorry for the bumpiness in the beginning, and it's always good to have you back. I think it's good to hear from people who are operating at the edge of what we understand in this field, and for the students. And I know I appreciate it. So thank you for doing it.
Thank you so much. Thanks.
Bye, everyone.